Hello, good morning to all of you. I hope all of you are doing well. So in today's class, we'll start with the fundamentals of the microprocessor. And to begin with, we'll try to understand what a microprocessor is. So a microprocessor, which is also known as CPU or central processing unit, is a multi-purpose, programmable, clock-driven, register-based computational engine that is fabricated on a single chip. It reads binary instruction from storage device known as memory. It accepts binary data as input and processes it in accordance with the instruction and generates the result. Now, a microprocessor is called as a multi-purpose device because it's capable of performing multiple types of operations governed by its capabilities. Now, a microprocessor is called as a programmable device because with each and every microprocessor, there is a set of well-defined instructions that can be used to write a program for attaining certain objective. A microprocessor is called as a clock-driven device because with each and every clock signal, a microprocessor is capable of initiating an activity. A microprocessor is called as a register-based device because all of the operations that a microprocessor performs, it performs in aid with the CPU registers that are defined in it. Now, all of these components in case of a microprocessor is fabricated onto a single chip. Now, a microprocessor is capable of reading binary instructions that are stored in the cells that are called as memory. It is capable of accepting input in form of binary. It's capable of processing the input as per the instruction, and it's capable of generating certain valuable result. Now, there are three different important characteristics that differentiate one microprocessor from another microprocessor. The characteristics are instruction set, bandwidth, and clock speed. Now, instruction set. With each and every microprocessor, there is a set of well-defined instructions associated with which can be used in order to write a program for attaining certain objective. Bandwidth, it refers to number of bits processed in a single instruction. Likewise, clock speed, it's often expressed in hertz. Clock speed determines the number of instructions per second the microprocessor can execute. Now, there are various types of instructions that are associated with a microprocessor. Now, based on the types of instruction, a microprocessor is typically capable of performing three different types of activities. First activity includes arithmetic and logical operation. So a microprocessor performs arithmetic operations such as addition, subtraction, multiplication, division, and logical operations such as realization of AND, OR, and NOT gate. Now, some of the sophisticated microprocessors or advanced microprocessors are capable of also performing floating point operation. Now, the second type of activity a microprocessor performs is it transfers a byte from one specified address location to another address location. The third type of activity a microprocessor performs is that based on certain decision, it transfers control from one location to another location in a particular program or a new set of instructions in a particular program. Now, all of these are possible with the help of the number holding area. These are called as registers. So, the operations that the microprocessor performs are done in aid of the CPU registers that are defined with it. Now, to summarize it, a microprocessor performs arithmetic and logical operation, a microprocessor performs a data transfer operation, and a microprocessor performs control transfer operation. Now, depending upon the evolution of the microprocessors are basically categorized into 5 different categories, namely first generation microprocessor, second generation microprocessor, third, fourth, and fifth generation microprocessor. Now, to start with the first generation microprocessor, the microprocessors that were introduced in between the year 1971 to 1972 are referred to as first generation microprocessor, wherein the instructions were executed one after the other in a sequential manner. Now, this kind of execution is also referred to as instruction interleaved execution between the various instructions. So, in this type of execution, the microprocessor updates the instruction pointer and fetches the instruction that is to be executed next so that the instructions are sequentially exhausted. So this considerably reduces the capability of the microprocessor in terms of throughput. Now, this led to the evolution of the second generation microprocessor. The microprocessors that were released in the year specifically 1973. Now, in this category of microprocessors, the transistors were made available on the IC chip with the sophisticated techniques such as 16-bit arithmetic operation and pipelining instruction processing, where the processors were defined, or the generation the generation of the microprocessors were defined by overlapping fetch, decode, and execution step. Now, in case of pipelining instruction processing, while the instruction is being executed, the next instruction is being fetched and prepared for processing. Now, the basic distinction between the first and the second generation microprocessors were the use of the semiconductor technology, which helped in increasing the instruction execution, as well as helped in increasing the chip density. Now, let us try to understand what a pipelining is, right? So, an instruction pipeline is a technique used in design of computer and other digital electronic device to increase the instruction throughput of the microprocessor. Now, instruction throughput basically refers to the number of instructions that can be executed in a unit of time by the microprocessor. Now, the important thing that you need to remember is that pipelining does not reduce the total amount of time required for executing instruction. Again, I'll repeat it. Pipelining does not reduce the the amount of time that's required to complete an instruction. Instead, what it does is it tries to reduce the execution time of the set of instructions by reducing the delay between execution of two successive instructions. So here, by reducing delay, what we are trying to do is we are trying to increase the throughput of the microprocessor. Now, a pipelining basically has 5 identifiable phases. The phases are instruction fetch, instruction decode, operand fetch, operand execute, and operand store. Now, instruction fetch, which is of 1 cycle latency, aims at fetching the instruction that is stored in the cache. Now, once the instruction has been fetched, in the instruction decode cycle, the instruction is decoded. That is, the instruction is to be understood what is the type of operation that is to be performed, because a combinational circuit has to be implemented for it. Now, once the instruction has been decoded, then what we need to do is we need to determine the operands that are participating in realizing the instruction. That is done in the third phase, that is operand fetch. So in operand fetch, the operands that are participating in execution of instructions are fetched. Now the next phase that we have is instruction execution, or the operand execution. So whenever the instruction fetch, or instruction decode, operand fetch is over, then what we need to do is we need to execute the instruction, or we need to perform arithmetic and logical operation on the operands that are being fetched. So while executing an instruction, we need to also keep in mind what are the various latencies that may be influencing the execution of the instruction. That is, the execution of an instruction may involve register operation, or may involve memory referencing operation, or it may involve multi-purpose instruction cycle. So whenever register operation is being performed, the operands are participating in the instruction execution are present in the register. So associated latency is to be taken care of. Likewise, whenever memory reference operation is to be done, the memory is the operand that are participating is present in the memory. So the virtual address is to be created and the memory access is to be done. So the associated latency is to be taken into consideration. Whenever multi-purpose instruction cycle operation is being performed, we need to take care of the latency, such as what kind of operation we are performing, multiplication or division or floating point operations, so on and so forth. So various latencies that are attributing to the execution are also to be taken care of. Now, once the execution is over, then what we need to do is we need to store the result of the operation to the memory location. So the fifth phase is operand store. So these are the 5 important phases that we have in case of pipelining architecture. So this particular diagram simplifies the representation of the various phases across various instructions. So there are timestamps along one dimension, and the other dimension we have the number of instructions. So in each instruction, what we have is we have the 5 important phases: instruction fetch, instruction decode, operand fetch, instruction execution, and operand store, right? In case of pipelining architecture, the instructions are executed in phase interleaved manner, whereas on the contrary, in case of the previous architecture, the instructions are executed in a instruction interleaved manner. Now, to further understand what is pipeline and non-pipelined architecture, so let us consider the execution of 3 instructions I plus 1 and I plus 2. So these three instructions are to be executed in a pipelined architecture as well as a non-pipelined architecture. So let us consider first the instructions are executed in a pipelined architecture. So in case of pipelined architecture, the instructions are executed one after the other. So let us consider Tn is the time that is required for executing an instruction and Tp is the time required for executing a phase. So for executing the set of instructions, we require 3 into Tn amount of time. Right, again I'll repeat it. So here we'll be requiring 3 into Tn amount of time because there are 3 instructions that are to be executed, or we'll be requiring 15 instances of Tp for executing the set of instructions, right? So if there are n instructions, we'll be requiring n into Tn amount of time for executing the set of instruction. Now on the contrary, let us consider the same set of instructions are executed in a pipeline architecture. Right, again, so I plus 1 and I plus 2 are executed in the pipeline architecture, right, again. So here what we have is we have the instructions being executed. Whenever one instruction is being executed, the other one is being fetched and prepared for execution. So here the execution is rather phase interleaved. Okay, so the total amount of time required will be 7 instances of TP, which will be required for completing the execution. So 7 is considerably less than that of 15. So here you see the instruction throughput in case of pipeline architecture is considerably high compared to that of instruction throughput in case of non-pipelined architecture. Now, to further elaborate, let us consider the following instances, right? So there are 5 phases: instruction fetch, instruction decode, operand fetch, operand execute, and operand store. And the other dimension, we have the timestamp. So we have 10 units of time, okay, across which 6 instructions are being executed. So there are 6 instructions starting from I1, I2, I3, I4, I5, and I6, right? Okay, so these 6 instructions are to be executed. Now just see, for execution of 6 instructions, we will be requiring 10 units of time. Okay, and the instructions are executed over 5 phases. So let n be the number of instructions, okay, and k be the number of phases. So here n is the number of instructions, so n is 6 here, and k is the number of phases. The number of phases are 5 here. So if I want to establish a relationship between the number of instruction, the number of phases, and the total amount of time required for execution, so the relation will be n plus k minus 1, that is 10. So n is the number of instruction, n is 6 here, k is the number of phases, that is 5 here, and minus 1. So 6 plus 5 minus 1 is 10. Right, so this is the way how what we do is we try to determine the total amount of time required for executing set of instruction in case of pipelined architecture. So in case of non-pipelined architecture, it was n into Tn. So n is the number of instruction and Tn is the time required for executing instruction. Whereas in case of pipelined architecture, it will be n plus k minus 1, where n is the number of instruction, k is the number of phases, and n minus 1. Right. So this is the relation that we have. Now, to further elaborate on pipelined and non-pipelined architecture, so we'll take into consideration 4 important characteristics. Okay, that is the speed up ratio, frequency, efficiency, and throughput. Right. Now, let us start with the speed up ratio. What is speed up ratio? Speed up ratio is the ratio of execution time in a non-pipelined architecture by execution time in a pipelined architecture. So speed up ratio S of k is represented as non-pipelined execution time by pipelined execution time. So which is equals to, as we have already determined, n into Tn is the total amount of time required for executing n instructions in a non-pipelined architecture, where Tn is the time required for executing n instruction. So it will be n into Tn. Likewise, in case of a pipelined execution, we have n plus k minus 1, right? The time required for executing the number of instructions. So now here let us try to understand what is this tau. Now tau is the total amount of time required for executing a particular phase, because in case of pipeline architecture we are executing in a phase interleaved manner. So tau is the time required for executing a phase. So tau is influenced by 2 important factors. One is the phase execution time, and the delay that is between the two successive phase execution because of the latches, implementation of the latches, right? Again, so pi and let pi and pi plus 1 be the two phases. So pi plus execution, between the execution of the two phases pi and pi plus 1, there is a delay because of the implementation of the latches between them, because output of one of the phase should go to the input of the to the next phase, right? So tau is attributed by the phase execution time, that is tau n, and the latch delay, that is tau d, right? So tau is the sum of tau n and tau d. That is the attribute take into consideration the phase execution and the delay, right? So now here in generic context, tau is estimated as tau is equals to maximum of all the tau i's, right? Because different phases may require different amount of execution time. So for example, instruction fetch, instruction decode, operand fetch, operand execute, and operand store may not take same amount of time. So different phases may take different amount of time. So based on that, a generic equation is formulated where tau is equals to maximum of all the tau i's, okay, maximum of all the time required for phases plus tau d. So this is a value, right? Okay, tau d is the delay. So it will be max of tau I plus tau d. So tau is estimated as max of tau I and tau. So this is a very important relation or expression that you need to understand, right? So in situation where n is considerably greater than that of k, where the number of instructions is considerably greater than that number of phases, then n plus k minus 1 can be approximated to n, okay? So when number of instruction is considerably larger than that of the number of phases, then n plus k minus 1 can be approximated to n. So sk can be represented as, in simplicity, it can be represented as n into tau tn, that is n into the time required for executing a particular instruction. So this is execution of n instruction in a non-pipeline architecture by n into tau. So here n plus k minus 1 is being replaced by n, so n into tau. So n cancels each other. So speed up ratio can be expressed as Tn by tau. Now frequency. So frequency is a very simple, has a very simple representation. Frequency is equals to 1 by tau, right? Now efficiency is equals to speed up ratio by the number of phases, right? Speed up ratio by number of phases. So we have expression for speed up ratio. The speed up ratio is equals to non-pipelined execution by a pipelined execution. So this we have already determined in the first parameter. So here now this Tn can be replaced by k into Tp, because Tn is the total amount of time required for executing a particular instruction. So for executing an instruction, you have k number of phases, and for each phase you require Tp amount of time. So k into Tp. So on further simplifying the expression, what we have is we have n into k into Tp, we have equated to tau, so n into k into Tp by n plus k minus 1 into tau by k. So if further simplifying it, we have n by n plus k minus 1. Right? So this is the expression for efficiency, n divided by n plus k minus 1. Now likewise throughput. So throughput is nothing but efficiency by the execution time, that is tau, right? Again, the phase execution time, that is tau. So tau 1 by tau is nothing but frequency. So throughput is equals to ek, that is efficiency into frequency. So that will be so we already have representation for efficiency. So efficiency is n by n plus k minus 1. So the representation for throughput would be n into f by n plus k minus 1. So these are the four important attributes that we need to discuss whenever you are discussing pipelining architecture, right? That is speed up ratio, then frequency, then efficiency, and then followed by throughput. Now, there are a few notable advantages of pipelining. That is, it increases the instruction throughput. Okay, it reduces the cycle time of the processor, and so on and so forth. So you can go through the advantages and disadvantages of pipelining. So here disadvantages basically discuss if you do not follow any pipelining architecture, what are the consequences. So you can go through it, right? Now, after discussing the first and the second generation microprocessors, we came to know how the transition has taken place to increase the instruction throughput, we have moved on from instruction interleaved execution to phase interleaved execution. Now, the third generation microprocessors were introduced in the year 1978. For an example, my Intel 8085 and Zilog Z8000. So these were the 16-bit microprocessor with microcomputer-like performance, right? So here, in case of third generation microprocessors, the number of IC transistor count was basically in the order of 250,000. Now, let us move on to the next generation, that is fourth generation. The fourth generation microprocessors, such as 960CA, that is Intel 80960CA, and Motorola 8800. These had ICs in the order of millions of transistors. Okay, so this is the way how the evolution has been taking place, right? So in the fifth generation, the number of transistors surpassed almost 10 million transistors. So just see, what you can do is you can go through the various generation of the microprocessor briefly. So here the things that you need to remember is that how the transition from instruction interleaved to a phase interleaved execution has been made. Okay, and what are the characteristics of the various the microprocessor, the various generations of the microprocessors, starting right from the first generation to the second generation to third, fourth, and fifth generation, and what are the IC counts that were there in the various generation, and what were the various years in which they were released. So these are the few important attributes that you need to remember in case of various generations of microprocessor. So let us move on to the next important aspect that we have to discuss in case of microprocessor fundamentals is that the way how the orientation of the computational system is done, right? Again, so now a typical computer that has a microprocessor in it, right? Again, so what it has is it has a control unit, it has an arithmetic logical unit, it has input unit, it has memory unit, it has output unit, it has a secondary memory, right? So this is a typical architecture of a computer system, right? Again, which has a microprocessor in it. So a microprocessor has in it a control unit, arithmetical unit, and associated registers. Okay, so application. So this is a typical representation of a computer system that you need to remember, that has in it a set of microprocessor, input devices, memory devices, and output devices. Okay. Now, application of microprocessor, you can go through it. So we have a reprogrammable microprocessor, we have embedded microprocessor. So reprogrammable microprocessors are used for executing different programs at different point in time, whereas embedded microprocessor, these are capable of performing same set of operations over a period of time. Let us consider a home automation system. So microprocessors that are governing home automation system, or second example, or washing machine. So these are embedded in nature, whereas a microprocessor that is running a normal computer. So these are reprogrammable in nature, right? Again. So now an important thing that you need to further note is that a microprocessor has in it a control unit and ALU on the same chip, whereas a microcontroller, right, has microprocessor, control signals, memory, I/O, and peripheral device, and on a single chip, and it has a mechanism to interact with the peripheral devices, right? Okay, so timers and converters, so on and so forth. So now here, these are the two important aspects that you need to understand. So difference between a microprocessor and microcontroller. So microcontroller has in it CU and ALU, whereas microprocessor has in it CU and ALU, whereas a microcontroller has in it microprocessor, control signal, so memory, IO on a single chip, and way for interacting with peripheral devices, right? So this is these are the things that you need to know whenever we're discussing the basics of the microprocessor. So in the next class, what we'll move on with is we'll move on with the various microprocessors that had evolved with respect to time. So thank you very much.